For lesson 2 in chapter 7, for properties of rational exponents, the thing that we need to start with is we need to go back to our regular exponent rule. So this was a handout that we did when we were learning initially about exponents and looking at different properties. We had the product, power of a product rule, so distributing it through fractions, quotients, and things. And as you can see, we've added these nth roots and these fractional exponents. Basically, these are the two ways of showing that we can go back and forth. That if we have a base with a fractional exponent, that the bottom number is our index, and then the top number is just going to be a 1 on the inside. Or if we have two of them, our bottom number is still our index, and the top number is an exponent for the whole thing. Now, with that, we're going to take that information that we already know about exponents, and we're just going to keep adding more things. So now how do we do that? Now that we have these new fractional exponents, also can be called rational exponents. So why would they be called rational? In your book, we have this term, rational. Remember, we've always talked way back at the beginning when we had our the circles and it looked like the solar system. And we had counting numbers, whole numbers, integers, rational numbers. So our real number system, we said rational. Often we think of that as in crazy or not crazy because we have rational numbers and irrational numbers. Well, it doesn't really have anything to do that. It has to do with this word ratio. So they're called rational because they have ratio. So then let's consider, why are they now calling these fractional exponents rational exponents? Well, they are written like a ratio. And since it's written like a ratio, we're going to call it rational exponents. So that's where the terminology comes from. And so it's the exact same thing when you're looking in your book, or if you're looking online or working in your homework, that we can call rational exponent the same as a fractional exponent as well. And it's that ratio that goes between how much I need and how much I have. And that's the part of the root system as well. So we learned, like I said, and I pulled up that exponent rules sheet. All of our rules in chapter 5 still work. They never go away. They never not work. Okay. And so what we can end up doing is we get to apply all of those same rules when we have rational exponents or fractional ones. So we know initially when we were working with multiplying the same base with two different exponents that we add them. That's one of our exponent rules. We know a power to a power is multiplied. We know that when we have two bases and we have a number on the outside, that we distribute it. And then we also knew that if we had a negative exponent, we change sides so that we can change the sign. So we apply all of those exact same rules to our fractional exponents. So when we have our bases the same, so here we have bases of 3, we have different fractions, we can add those fractions. Now, the trick is we have to go all the way back to Algebra 1 or pre-algebra and remember that our fractions have to have a common denominator to be added. So yes, we can always add them, but then again, we're going to have to use our fraction rule, making sure our fractions have common denominators. In this case, 1/2 plus 3/2 gives us 4/2, which then gets reduced down to 2. So we're gonna add them and then we're gonna reduce it as much as we can. We have the power to power, works the same. So our 3/2 power is then multiplied times the 2. So 3/2 times 2 gives us 6/2, which again, we're going to reduce down to a 3. In this case, we have 9 times 4, and then we're taking the square root of it. So our 1/2 will get distributed to both of them. And then we would say the square root of 9 is 3, and the square root of 4 is 2, so our answer would be 6. And 25 to the 1/2, we're going to make it positive because we like to have positive signs, so we're going to change sides on that. So again, same rules that we used when we had regular integer exponents, we can use the exact same rules when we have fractional exponents. So on these, when we're looking at it, we have the same base, so yes, we can add our two fractional exponents here. For these, we would take our -1/4 and distribute it to each one. And since we're multiplying times 4, the 4s are going to cancel out. So we're just going to have a -1. We also get to look at our quotient rule. Remember, for our regular rule, it was whatever you have on the top. So if you have, x to the m over x to the n, when they are divided, then our exponents are subtracted. So m minus n, same thing for that, as long as they have the same base for them. We also looked at if we had the square root of 3 over the square root of 2. Since our indexes were the same, we could combine it all under one radical. And then sometimes that helped us simplify a little bit faster. So on number 5 here, they both have 1/3, so they both have the cube root as their index. And so we could rewrite this as 12 over 4 as a cube root. And this entire thing is now squared. Okay. So what I did here is I saw that our exponent, our fractional exponent here is exactly the same. It is a cube root of 12 over a cube root of 4. I can't do either of those, but I can combine this. 12 divided by 4 is 3, so that was super easy to simplify. So now I have a cube root of 3 squared. Now, when we have this, it's important to note that often they will write for the fractional exponents. Let me pull that up again. For this fractional exponent, you see right here it has m over n, and then we've got our index, which is the denominator, and then we have our numerator is now this exponent on the outside of a parentheses. So you might say, well, Ms. Thomas, why can't I write it on the inside of the parentheses? Well, you really can, because what does it mean when it's on the outside? It means we'd have a cube root of 3 times the cube root of 3. We have both of them. And because of our root rules, we know when we have a multiplication with the same index, we get to combine what is underneath. So we could write it as the cube root of 3 squared in that way. And so now we know that our base is 3. I have 2. I need 3. And so now I have 3 to the 2/3 as my exponent. So hopefully you can see that all of our previous rules are working together with all of the rules that we have now. Same thing. So if we are, gonna skip through those examples from class. Okay, so this is something that I want to hit. When you have an index, when you have an index, so in this case, the index is the instructions for how many I need for my root. This is my root index. This is giving me instructions for my radical versus a coefficient. In this case, my index is not shown. My index would be an understood 2. So make sure that when you are writing that your placement matters, that if you have a cube root of 16, that you are not writing it like that, because this is 3 times the square root of 16 versus the cube root. I am fine, and I know that don't have the best handwriting. Often it's written where it sits right on the line. It can be written where it's in the crack of the V, just so that there's a definition that this index goes with this radical, and it doesn't happen to be a coefficient that is placed out front. So that's an important thing to note as you are working through, to notice in your work, to notice in your handwriting as well. Okay, so adding and subtracting. What did we have when we had square roots? Well, to add and subtract, same way if I have x plus 2x, every part of that variable had to be same. If I had x plus 2x squared, these are different families. Different families cannot add together. Different families can multiply, but different families cannot add. So when we are looking at adding and subtracting, we are back to looking at like families each time. So if I have 2 cube roots of 4 and a cube root of 4, and I want to add them together, and I decide to add them, my entire family is this cube root of 4, and I have another cube root of 4. So we could technically replace that with an x. So now I have 2x plus x. That would give me 3x. So in this case, this would be 3 cube roots of 4. Yes, they can add together. They are like radicals. They have the same index and the same base. So they can work together. Now in this case, we have the cube root of 4 and the cube root of 2. I do have like indexes, same index, but I have a different base. So this would be like saying, you know, x cubed plus y cubed. Like those are not going to add together. So we cannot add them if they do not have the same index and the same base. Okay, so that applies here. It also applies for fractional exponents. So in this case, I have 7 as my base with a 1/2 exponent. So really I'm looking at the square root of 7, correct? And then I have 3 times 7 to the 1/2. So this would be 3 square roots of 7. So again, like bases, like indexes, I could multiply, or I could add these together, and I would have 3 plus 1, because this is really a 1 up front, and I would end up with 4, 7 to the 1/2. Okay, now in this one, I've got the square root of 7 plus the square root of 6. They have the same index. They're both square roots, but they are not like bases. I cannot add those together. Okay, here's a couple of more examples. In this one, we would be looking at maybe 7x plus 2x. I've got 6 to the 1/5 and 6 to the 1/5. They're the same base, same index, like families. So we can add those together. We simply add our coefficients, and we keep our variable in that case the same, or in this way, we keep our radical, our fractional exponent here the same, 6 to the 1/5. Okay, so now I have 9. And if we turned it into roots, in the same way, I just rewrote it as the 5th root of 6, 5th root of 6. We would add 7 plus 2 would be 9. And our entire family, remember, we can think about that might be as 2 x's. If it's easier for you to think of that way, then go ahead and replace it with a single variable. 7x plus 2x would be 9x, but our x value is this 5th root of 6. Okay. Same thing for subtraction. Now, the important thing to remember for subtraction is that subtraction always goes with everything. So if we are now subtracting, remember, if we were subtracting multiple radicals, this negative would need to go with all of it. So we need to distribute it across with that. So we don't want to get hung up on that. But in this case, we have cube root of 16 minus the cube root of 2. Well, the first thing is right now we cannot subtract them because I have like indexes, but I have different bases. However, there is always the option we want to ask ourselves, can we make them like? can I make the same base? Because when I'm looking at the cube root of 16, it's not fully simplified because 16 is 2 times 2 times 2 times 2. It's 2 to the 4th. That means I have enough to have part of it escape. So if I were to simplify the cube root of 16, I would then have 2 cube root of 2. Now, as we look at it, I have like indexes and like bases. I have like families. So basically, I've got 2x minus x, which would give me just 1x. So my x is this. So I've got 2 minus 1. That's going to give me a 1, and I'm just going to have my cube root of 2. So in this one, when we first looked at it, we thought, nope, can't do anything with it. However, we were able to apply our simplifying rules and make them like, and then be able to work towards that. So again, we're just using more of the tools that we have from our toolbox. Same thing for this one. It applies for all of the variables. If I have the cube root of 125y to the 6th, I can write it all out, 5 cubed and 6 y's, and say I need 3, I have 3, and they can escape in groups of 3. Or I could have just rewritten it as 5 cubed times y squared cubed, because I have 2, or I have, if I broke it up like this, I would have y squared, and I would have 3 of them, 3 of those sets. So y squared gives me cubed. This is also a power to a power, so y squared cubed is to the 6th. So whenever we're breaking up our numbers, like if I'm breaking up 6 and I have an index of 3, if I get a choice of how I'm going to break up 6, I'm going to make sure that it has a 3 so it can cancel out. Well, so if my outside one is 3 to cancel, that means my inside one has to be 2. So we get to use the tools that we know about math and multiplication and factors and make things work the way that we want them to help simplify. So in this case, we know that when something is multiplied and it has the same index, just as if it had the same index here, same index, when they're multiplied, we multiply what's underneath. So this would be 2x, cube root of 2x. If we got there, we can undo it. So every time we go forward, we can always go backwards. So in this case, I'm looking at it and I've got, hey, I've multiplied, which means I can divide and separate them back out. So I just separated them into their individual little radicals. I need 3, I have 3, so I simply have my base of 5. I need 3 here, I have 3, and my base is y squared. So 2 different ways to accomplish the same thing with our variables, okay? When we have quotients, this can often be the hardest. The first thing that we're going to want to do is apply our quotient rules. Now, I know initially when we are working with quotients, we look at it and we say, uh-oh, we have a negative. We don't like having negative exponents. Let's make them positive. We change signs, we change sides. However, because our quotient rule deals with that subtraction, sometimes it can be a part of it. So personal preference, if you want to make them positive in the first place, you're welcome to do that. If we want to use our quotient rule, we can do that as well. So we know that if we have this whole amount here, we're going to have our 6 over 2. That's going to be our number portion, will be our 6 over 2. Our x's, I have x to the 1 here, and then an x to the 1/3 on the bottom. I know that for my quotient, when they're on top of each other, I subtract them. So I now have x to 1 minus 1/3, okay? My y stays the same here. And if I don't have a z, and I have a z on the bottom, remember that this is really a 1. Anything to a 0 power is 1, so I technically could say I've got 0 to the z to the 0 on the top. And then I would have 0, 0 minus a negative 5. We also know that from our negative exponent rule that when we change sides, we change signs. So when we move our z up to the top, it's going to become a positive. So it should be positive in the end. But I did want to show you that we can replace any number 1 with a variable to the 0 power if that needs to help us. And so then when we're subtracting, we have 0 minus, we're always subtracting, and this one happens to be a -5. So that's why initially why it does work according to the quotient rule. So now we've got our different parts and we're going to simplify. So 6 divided by 2 gives us 3. X 1 minus 1/3, so 3/3 minus 1/3 gives me 2/3, so that gets to stay the same. My y to the 1/2 stays, and my z has now become a +5. So that's how we would simplify a quotient. Okay. So for these, we could break each section up, or you could look and say, which ones can I pull out? So I need 5. I have 5 of my A. So my A in this case is going to pull out. I need 5. I have more than 5 of my B, so I can take out 5 of the B. Comes out, and it leaves me with 4. So I'm going to have 9 minus 5. So I'm going to have 4 B's left over inside. In this case, I've got 13 C's, which would be C to the 5th, C to the 5th, 5, 10, 13. So I could take out one of them. I could take out another one of them. And we would have A, B, C squared on the outside, and a 5th root where our 5 is left, our B4 is left, and our C cubed is left underneath, right? So for this one here, it's important for us to remember back to our rules that we were working through. We could separate this out again, right? Cube root of x over the cube root of y to the 7th. Well, I need 3 and I have 7. So how many was that? That's y3, y3, and an extra y gives me 7. So this one comes out, and this one comes out, and this one stays underneath. So when we're looking at it, we have y squared cube root of y over cube root of x. Now, we know that we cannot leave a radical in the bottom. So I have y squared on the outside. And I'm going to combine these back together as the cube root of x over y. I need 3 to be able to get this y out. Well, I only have 1, so I need 2 more. So we're going to use our math rule that when we multiply by the number 1, we're not changing anything. So I can multiply anything by the number 1. Well, I need 3 of them, and I have 1, so I need 2 more. So I'm going to put y squared and y squared. So y squared divided by y squared is the same as the number 1. I'm multiplying both the top and the bottom. So now on the top, I have the cube root of xy squared. And then on the bottom, I have the cube root of y cubed. Well, my index and my exponent match. So these come out together. So we end up with the cube root of xy squared over y squared times this new y, so y cubed in that case. Now, what we could have done as well is we could have left it here and said, if I need 3, that means all of my exponents have to be multiples of 3. Well, multiples of 3 are 3, 6, 9, 12, going forward. Well, I have 7. I can't go down, so the next one up is 9. I want to get my y 7 to a 9, and that way I have a multiple of 3. So we would do y squared. Again, remember this is the number 1. Anything divided by itself is the number 1. So now I have the cube root of xy squared over y to the 9th. Okay? Which can be separated into the cube root of xy squared And now I have the cube root of y to the ninth. If I rewrite that as a fractional exponent, it helps me simplify it faster. 9, I have 9, I need 3. 9 divided by 3 is 3, y cubed. You could also write it as y cubed, knowing that I want 3 to be one of the numbers I'm multiplying by. So if my 3 is on the outside, 3 times 3. And then you know your base is y cubed. Either way, but sometimes it's easy to just switch it to our fractional exponent because we can simplify that one a lot faster. Okay, so those are some examples there. So again, as we had looked before, when we are simplifying expressions or equations with roots, we always want to simplify our radicand down. That way we can be confident that they either are alike or they're not alike. Because, you know, sometimes they look like they're not alike, but when we simplify them, they really are alike. So in this case, I had the cube root of 5x to the fifth. Well, I have more than 3, so I went ahead and took out an x and left the extra 2 in there. In this case, I've got 40, which is 8 times 5, and 8 is a cube root, so that one's fun. So it comes out as a 2. I have, and then I leave my x squared underneath it. And so again, we were able to take our roots here that initially were not like, and once they are simplified, now they are like. And since they are like, we can do 3x minus 2x, which leaves us with 1x. And then our entire like family stays the same. Cube root of 5x squared, cube root of 5x squared. Remember, we are just replacing our variable with our entire family. So always be sure to look at it and say, it doesn't look like I can do anything. Oh, can I simplify? Could they be alike? Now, okay, we're going to do a couple of real life ones. So in this case, there was a, when we compare different animals, their surface area size is related to some constant for their species type times their mass in grams to the 2/3 power. So if we have this thing, it says approximate the surface area of a cat with a K value of 10. So if this is our K, it's going to be 10 and a mass of 5 kilograms. Well, the first thing we need to notice is the mass here says mass in grams, and they gave me mass in kilograms. So I've got to take 5 kilograms and change it to grams so that I know that 1 kilogram is 1,000 grams. My units cancel out, and so now I have 5,000 grams to the 2/3 power. Now this is important. This is where it's important, where we had that little section on scientific notation. If I replace 5,000 with 5 times 10 to the third as scientific notation to the 2/3, do you now see that we have something that could be multiplied, and we have a fractional power to a power that's going to cancel out? So let's look at what that works out like. So we have 10, and then we changed our 5,000 into 5 times 10 to the third, and it's that whole thing to the 2/3. So I'm going to distribute, use my power, so now I have 5 to the 2/3 plus 10 cubed to the 2/3, and I'm going to simplify that way. So I've got 10 times 5 to the 2/3. We used a calculator to get approximately 2.92. And in this case, I have 10 to the third times 2/3. So 3 times 2/3 gives me just squared 10 squared. So now I have 2.92 with 1, 2, 3 zeros. I'm just going to move my decimal 3 places, 1, 2, 3, and add a 0, and I have 2,920. So approximately 3,000 centimeters squared on that one. So that's how our fractional exponents in this case, since we were using scientific notation, it was a lot faster to leave it as a fractional exponent than it was to turn it into a root in that way. Okay, so the big wrap-ups for 7.2 is using all of our exponent properties that we knew from our regular exponents and being able to apply those to our rational/fractional exponents. So this says if we know that 46,656,000 is 2 to the 9th times 3 to the 6th times 5 to the 3rd, what is the cube root? Well, if I'm taking the cube root of each of these, the fastest way would be to turn them into fractional exponents. So I have 2, I have 9, I need 3. For the 3, I have 6, I need 3. For the 5, I have 3, I need 3. And immediately, my 9 over 3 becomes squared. So I have becomes cubed, 2 times 3. 2 to the 3rd. My 6 over 3 becomes squared, so 3 squared. My 3 over 3 becomes a 1. And I have 8 times 9 times 5. So we were able to quickly reduce that down. And so then you'd have 40 times 9. 9 times 4 is 36. So 360. So we can see how using our fractional exponents allowed us to find that answer much faster than actually multiplying it out and finding the cube root. For this one, we could separate out into the different parts. Since 16 and 81 can't be simplified as a fraction, we can simplify them as individual radicals because the 4th root of 16 is 2, the 4th root of 81 is 3. In this case, these are not like, so we cannot subtract. However, 200 is 2 times 100. And I know that 100 is 10 times 10. And this is a square root and I needed 2. So that comes out and now I have 10 square roots of 2 minus 3 square roots of 2. I now have like families and I can subtract 10 minus 3 is 7. 7 square roots of 2. And in this case, we're going to look at our family. And I have the 5th root of A and a 5th root of A. And I can say those are like families. Same index, same base because it's addition and subtraction. So I'm just going to do 2 minus 6 gives me negative 4. And then A to the 1/5 stays. So let's look at some of the homework for 7.2. Okay. So 22 through 33 just says to simplify the expression. So when we have ones like 22 and it says 3 to the 5/3 times 3 to the 1/3, I first look and say multiplication. Well, the only rule for multiplication, the bases don't, is that the bases have to be the same. So in this case, my bases are the same. So I'm simply adding these together. So I have 5/3 plus 1/3 gives me 6/3, which reduces to 2. So I have my base of 3 squared, which is going to give me 9 in that case. 23 has us doing 5 to the 2/3 times 1/2, raised to the 1/2. So this is a power to a power. We know that for power to a power, our base stays the same, and we multiply our exponents. So you could multiply it and get 2/6, or I could say I've got a 2 on the top, 2 on the bottom. And so now I have 5 to the 1/3. And that can just stay written like that. Completely fine. 25 has 1 over 36 to the negative 1/2. So the first thing that we notice is that we've got a negative exponent. So let's change sides and change the sign. So now I have 36 to the 1/2. 1/2 is the square root of 36. We know that 36 is 6 times 6. I need 2. I have 2. Square root of 36 is 6. We could rewrite it as 36 being 6 squared raised to the 1/2. And knowing with our power to power, I now have 2 times 1/2, which gives me 2 over 2, which gives me 1. And 6 to the 1 is simply 6. So there's that one to work out. And then let's look at this one. So 32, we have 12 to the 10/8 over 12 to the negative 3/8. Okay, let's pay attention on this one. We have the same base. When I have the same base as a fraction, we can apply the quotient rule. The quotient rule says that I have to subtract. So the top one, which is 10/8, we then subtract the bottom one. In this case, the bottom one is negative 3/8. It is very important when we are using the quotient rule that we are subtracting the entire number that's on the bottom. And if it's a negative, that means we now have 2 negatives. Because easily we could say, oh, we're subtracting and get 7/8, but that's not going to be the right answer. Because when we subtract a negative 3/8, they have the same denominator. So now I've got 10 plus 3, and I've got 13/8. I've got 12 to the 13/8. Another way to do that is we could have had 12 to the 10/8 and said, I don't like that fraction on the bottom. I'm going to move them to the top. So times 12 to the 3/8. When our bases are the same, we are adding our exponents together. And you would have also gotten 13/8 on that one as well. Okay, so for 22 through 33, those problems, we are just simplifying. Now, here's my rule. If it starts as a fraction, you can leave the answer as a fraction, okay? You don't have to change it into a radical. If it starts as a radical, you can leave it as a radical or you can change it to a fraction. But don't feel like you have to go back and forth, especially for these. So if it starts as a fraction, just leave it as a fraction. If they gave it to you as a radical, answer it as a radical. Okay, so properties of radicals number 34 through 41, again, they're just wanting us to simplify. But instead of having a single one, we are using a base with the fractional exponents, we've gone back to using the radical sign. So for 34, we've got the square root of 64 times the cube root of 64. Now, this is where it's important to look at it because we do not have the same index. So according to our radical properties, we can't multiply those. We can only multiply when we have the same index. So I'm going to switch it to fractional exponents. Because now that I have fractional exponents, my base is the same, and all I have to do is add the exponent. So now I can work it. So when it was written as a radical, couldn't work it, change it to fractionals, I can work it. So now I have 64 and 1/2 plus 1/3. Now these are our math rules. Our fractions have to have the same denominator, so that would be 3/6 plus 2/6, which now gives me 5/6, right? So I have 64 to the 5/6 in that way, okay? Let's see. 1/3. What do they have for that one? Okay, and then they actually want you to work that out. I'm fine with you leaving it as your fractional exponents as well. If we can reduce them, that's great. If not, then you can just leave it as a fractional exponent. Okay, so then let's look at 35. It's got the 4th root of 8 times the 4th root of 2. Again, we have the same index, but we have different bases. So, but in this case, it's multiplied. So since it's multiplied, we can combine them together. So we've got the fourth root of 8 times 2. We know 8 is 2 times 2 times 2. And then I've got this extra 2. I need 4, I have 4. My answer would be 2 for that one. Okay, and then let's look at 39. 39 says the cube root of 4 over the cube root of 32. So in this case, I can't reduce either of them with the radical on its own, but I have the same index. So I'm going to put them under the same fraction. Well, now I can reduce 4 over 32. They're both divisible by 4 as 1 over 8. Now that I have a cube root of 1 over 8, I can take the cube root of 1 is 1. The cube root of 8 is 2. So now we were in one place, we weren't able to reduce it. When we combined it, we were able to reduce down to 1/2. So those are 34 through 41, how you need to work out those problems. For 42 through 49, it's just saying write it in the simplest form. So again, we are just simplifying. For 42, it gives us the square root of 50. And this is back to just our plain radicals. 50 is 25 times 2. I'm always going to be looking for something that has the same exponent. There, 25 is 5 times 5 times 2. We could have said it's 5 times 10 and broken that out. And so when we take out our 5, we've got 5 square roots of 2 for that one. When we are looking at, number 45, let's look at that one. 45. 3 times the fourth root of 24 times 5 times the fourth root of 2. Remember, this is all multiplied, and these coefficients really are multiplied as well. So I'm going to put all of my whole numbers together. So I'm going to do 3 times 5, and then the fourth root of 24 times the fourth root of 2. Well, because these are multiplied and I have the same index, we can combine those. So now I've got 15, 3 times 5, and the fourth root of 48. So then how do we reduce the fourth root of 48? So what is 48? I've got 24, so we knew it was 24 times 2. 24 is 2 times 12. And then I've got my 2. 12 is 2 times 6. 2, and then I've got 2 times 2. And then my 6 is 2 times 3 times 2. So I do have 4 2's in there. So now I have this 15 that stays on the outside. Now I've got this 2 I'm pulling out because I had 4 2's. And then I have a fourth root, and this 3 gets left underneath. Now we always go back and say, is there anything on the outside that we can simplify? 15 times 2 is 30. So I've got 30 fourth root of 3. So we're going to just keep using our tools in our toolbox to simplify. Okay, so for 50 through 55, it says combining roots and radicals. And so these are addition and subtraction problems. Remember, for addition and subtraction, both our index and our base has to be exactly the same. So let's look at 50. We've got fifth root of 6 plus 5 times the fifth root of 6. Yes, I have like families. I've got an index of 5, a base of 6. They're exactly the same. This would be the same as x plus 5x. So I've got 6x, or 6 times the fifth root of 6. Okay, let's look at 51. 51 says 5 times 5 to the 1/7 minus 7 times 5 to the 1/7. So again, my base is the same. My index is the same. This is just like 5x minus 7x. 5 minus 7 is -2. That would give me -2x. I've just replaced my x with my entire like family. So I have negative 2 times 5 to the 1/7. And that would just stay like that. Or you could rewrite as that the 7th root of 5. Either of those are acceptable. Okay. And then 54, let's do that one. The cube root of 375 plus the cube root of 81. So in this case, we're going to have to figure out what our factors are. And we're looking for multiples of 3 or factors of 3, all right? So 375 divided by 3 is 125 times 3. 81 divided by 3 is 27 times 3. And I know 125 is 5 cubed, and 27 is 3 cubed. That's why it's important to know our squares and our cubes. So in this case, I have 5 cube roots. My 3 was left over, plus my 3 comes out 3 cube roots, and my 3 here was left over. So now I do have like indexes, like bases. 5 plus 3 gives me 8. 8 cube roots of 3 for that. Okay, let's see. For your homework, for 56 through 67, we're simply replacing our base numbers with variables. Variables work exactly the same as base numbers, except that we don't actually end up with a real number answer in the end. So for number 56, we have x to the 1/3 times x to the 1/5. I'm multiplying, so only my bases have to be the same. That means I can add my exponents. So I have 1/3 plus 1/5. They need to have the same denominator. So that's 5/15 plus 3/15, and I get 8/15. So I would rewrite this as x to the 8/15 for number 56. All right. Let's look at number 61. We have the 4th root of x to the 12 over y to the 4th. Remember, we can separate these out. So the 4th root of x to the 12 and the 4th root of y to the 4th. Well, these match. I need 4, I have 4, so I simply have y on the bottom. Now on the top, if I wrote it as a fraction, I would say I have 12, I needed 4. 12 divided by 4 can reduce to 3. So I have x cubed over y is simply my answer there for number 61. Okay. And then let's look at number 66. It's 2 square roots of x times square root of x cubed over square root of 9x to the 10th. So in this case, they are all square roots. Since they are all square roots, we could combine them all as x times x cubed over 9x to the 10th. And then we can simplify. I've got x to the 4th on the top, 9x to the 10th on the bottom. I get to use my quotient rule here. 4 minus 10 gives me 6. So now I have 9 and then x to the 6th on the bottom. I have this 2 and I'm taking the square root. Well, the square root of 1 is 1 for this section. So I've got this 2 out front. Square root of 1, and I've got the square root of 9x to the 6th. 9 is 3 times 3. There's my 2. It comes out as a 3. X to the 6 is x cubed times x cubed. There's my 2. And it comes out, so I'd have 2 times 1 over 3x cubed. Oops, 3x cubed. So I have 2 over 3x cubed. All right, so just step by step working through those different parts. For 68 through 75, it says just write the expression in simplest form. So it's all about simplifying. Again, we're just practicing the simplification of this, making sure we're able to use all of our rules. for 68, when I have the square root of 36x cubed, I know I need 2. So I've got 6 times 6 times x times x times x. I can take out any groups of 2. So now on the outside I have 6x, and what stays on the inside is whatever's left over. And we're going to simply write 6x square roots of x. Okay. Now, number 73, we have the cube root of x cubed over y squared. So initially we have this fraction. It's important for us to look at the fraction and say, I have to rationalize the denominator. I cannot leave a fraction. So I need 3 and I only have 2. So I'm going to make myself have 3. I'm going to multiply by the number 1. So I'm going to do y over y is the number 1, and that gives me x cubed y on the top, and it gives me y cubed on the bottom. So now I have the 3. So when we separate it out, cube root of x cubed y over the cube root of y cubed, my index and my exponent match, so I simply have my base. Here I need 3, and I have 3 x's, so they get to come out, but my y has to stay underneath. And so we're going to simply write it x cube root of y over y, and that is completely simplified, the most that it can be. Right? For 76 through 81, it's about combining variable expressions. So again, we're looking at addition and subtraction. Our rules for addition and subtraction, they have to be exactly the same. So let's look at 76. If I have 2 fifth roots of y plus 7 fifth roots of y, indexes match, radicand there matches, so it's 2 plus 7 gives me 9, and then my like family stays the same. Okay, so for 79, we've got x to the 9th y all raised to the 1/3 plus x y to the 1/9 all raised to the 3rd. The thing that we want to do here is we want to go ahead and distribute out our fractional exponent there. So now I have x to the 9th times 1/3 times y to the 1/3 plus x to the 3 times y to the 3 times 1/9. Now 9 times 1/3 gives me 3, and I've got y to the 1/3 plus x cubed times 3 times 1/9 gives me 1/3. Okay, so now we see our families are alike, and I have 2 of them. So I'm simply going to have 2 of my x cubed y to the 1/3. So we were able to use our rules, simplify, and find like families for that. Okay. So 82 through 89 are bonus questions where we're just taking an extension of what we already had. I'm going to look at 82. For you, it says x squared times x to the square root of 3. If I was looking at this, I say I have the same base. So when I have the same base and it's multiplied, I'm just adding. So I'd rewrite that as x times 2 plus square root of 3. So we've combined it into 1. It's not tricky. We're not trying to trick on here. Let's look at 83. Y square root of 2 raised to the square root of 2. We know that when we have a power to a power, they're multiplied. So I've got the square root of 2 times the square root of 2. They have the same index. They can be combined. Or we also know that when we have a square root squared, it's simply the base underneath. So I could say I've got the square root of 4, or I could say I've got the square root of 2 squared, because I have both of them. Either way, I'm going to end up with 2. So the square root of 2 numbers squared, so I've got y squared in that case. So we're just using our same rules. applied a little bit further out for those extra ones. Now, for number 91, it says the area of two circles are 15 square centimeters and 20 square centimeters. So I've got one circle here where my area is 15 square centimeters, and I've got a bigger circle where my area is 20 square centimeters. I'm all about drawing stuff out. It says find the ratio of the radius of the smaller to the larger. Okay, so when they write it like that, it goes in order. Ratio of whatever they say first goes on top, whatever they say second goes on the bottom. So the smaller to the larger, and they want it in radius. So we need to figure out how to get radiuses in this. Well, right here for area, I know that a circle is pi r squared, the formula. So here I've got 15 equals pi r squared. And this one I've got 20 equals pi r squared. So my radius on the top, I'm going to solve for r of the small one and solve for r of my large one. So you need to take 15 equals pi r squared, and we're going to solve for r. How do we get r all by itself? On the bottom, we've got 20 equals pi r squared. Again, I'm solving for r. So my answer for r on the top, I've got 15. I'm going to divide by both sides by pi, 15 over pi, and I'm taking the square root of it. So we're going to do the same thing for the bottom, and we're going to set those up as a ratio. They are both square roots, which means we can make one giant square root of our numbers underneath, and then we can simplify that big fraction. So that's how you're going to work out number 91.